Hello all and welcome back to this course on computer organization. So having looked at the instruction format of the RISC V, let us now get into the implementation of what is known as a single cycle processor of the RISC V architecture. As mentioned earlier, I will be reusing the material and the slides of Professor David Harris with his permission for this course. So what we are going to now do is to actually look at implementation of the architecture of the RISC V, the computer that we studied. We are also going to jump into performance analysis, clock frequency, all the electrical parameters of the microprocessor as well. So what we are going to do here is look at the introduction, performance analysis, then we jump into the single cycle processor, multi-cycle processor, and then the pipeline processor. We will not have time to go into the advanced micro architectures, right? So basically the point is a micro architecture is, how do you implement an architecture in hardware, right? So we have discussed, okay, we want the op code, we want the instruction code, machine code to be like this, but now how do you take that to an implementation? What are the actual hardware elements that go into the implementation? And a processor typically has two key elements. One is the data path, how the data is actually going to flow in the processor, and another is a control path. The control path is basically the block that takes the machine code from the memory and is going to decode and instruct the processor to do certain operations in a certain order, right? That's the key point here. So like I said, there are three types of implementation. One is a single cycle processor. The important point here is every single instruction in the microprocessor will take exactly one clock cycle to implement. Okay. On the other hand, the single cycle process might be a little too slow because we have tried to make the slowest operation work in the single cycle. Maybe that's not the best way. So multi-cycle basically breaks it into smaller steps, and therefore you can speed up the clock, you can increase the clock frequency, right, and thereby speed up your execution time. The best and all processors today implement what is known as a pipeline architecture, where basically each instruction is broken up into a series of steps and multiple instructions are executing at the same time, right? Of course, it's not that they all try to compete for the same hardware block. No, they all work on different hardware blocks at the same time, and this is a very efficient process by which you can increase the clock frequency significantly, right, and improve what is known as the throughput of the system. So how do you measure processor performance, right? So let us look at it. We have studied the x86, we have studied the RISC, and we made an argument that x86 has too many instructions, the instruction set is very complex, and therefore RISC decided to reduce the instruction set with a very structured machine code and stuff like that. But really the proof of the pudding is in eating it, and therefore what really matters is not whether it the architecture sounds nice or is easy to implement. None of this matters. What really matters is if you are given a benchmark code, C code that has to be executed, what really matters is how fast does it execute on the x86, how fast does it execute on the RISC processor, right? Whichever is faster, it means it is going to be, that is a more efficient implementation, right? So therefore we have the execution time, which is the most important performance discriminator between architectures. What is execution time? It's basically, if I give you a C code, it compiles into some number of instructions. We have seen this, machine instructions, right? So number of instructions into the cycles per instruction, okay, because each instruction is going to take a certain number of clock cycles, right? Remember, in single cycle that is 1. In multi-cycle it could be different for different instructions, we'll come to that, and multiplied by the clock period, because an instruction takes so many clock cycles. You add all these clock cycles together and eventually you basically get what is known as the execution time, right? So it's basically number of instructions into cycles per instruction, CPI. Okay, so into CPI, as you can see here, into the clock period and the instructions per cycle, right? And of course the challenge is to satisfy the constraints of cost, power and performance. Performance is obviously speed that we are talking about. Okay, so let's now jump into this RISC V processor. What we will do is we will try to calculate the clock period and then come back and see, you know, how much execution time is needed for a particular program and so on, right? So look at this. So when we want to implement the RISC V, you know, there are many different instructions, right? So maybe 30 odd instructions which are there. We don't have to look at all of them. What we really need to look at is the different types of instructions, and that is only 5 or 6. Okay, so we are going to start with a subset of these types first and look at implementing them in hardware, and then we will add more and more elements to get to the entire, you know, instruction set. So let's look at the R type of instruction. Okay, we are going to look at only 3 subsets. One is R type, ALU instructions, add, subtract, and or whatever. Then we are going to look at memory instructions, and then we are going to look at you know, load word, store word, that's an instruction, and then we are going to look at branch and branch on equal, right? BEQ, which is basically, so what are these types of instructions? Basically we are operating on either registers, okay, and the ALU, where, you know, you add 2 registers, put the result back into register, or you take a register, add it, find the address, get the data from memory, put it into a register, or you take the value of a register, put it into memory. So this is the load and store respectively, right? And of course the other kind of instruction is the branching instruction, where the next instruction is now not going to be at PC plus 4, right? Remember, in RISC V, every instruction occupies 4 bytes. It's a 32-bit instruction. So therefore, normally next instruction would be PC plus 4. It's very simple to implement. However, when you have a branching, right, like a jump in x86, right, jump on no 0, here you have a BEQ, branch on equal. There you would basically have to take the new label, new address, and load it into the program counter. So this we have also seen in x86. That's why we are dealing with just these 3 subsets, because it covers all the aspects of the implementation that we want, especially from estimating the clock frequency. So the architectural state elements basically essentially determine, you know, everything about the processor, right? What you use, right? For example, if you were to implement an ALU using just NAND gates, technically it could be done, right? Because the NAND gate is universal, right? Well, the whole thing could just fall apart, right? Because it would take a woefully long amount of time, and therefore, you know, what you choose, how you implement is very, very important. Okay, basically there are 32 registers. Okay, likewise, how many registers you choose in your you know, in the register file, you know, the program counter, and then there is a memory. Okay, there is a memory block, there is a data memory, there is a code memory. These two are 2 different memories, as we will see, right? Though the 2 memories might be identical, like SRAM or whatever, right, technology wise, but they are 2 different instances of memory that are needed for implementing. So we have this kind of a thing here. You have the program counter, which is basically a simple 32-bit register. Okay, what is this going to do? It's going to store the address of where you have to go and fetch the instruction from. Therefore, this program counter is now going to talk to an instruction memory. You give an address, you get the data out of it. So you give the program counter will give the address, the instruction memory will then read out the data onto the data bus, RD bus, which is again 32-bit. Remember, we had discussed this. The address is 32-bit, data is also 32-bit, right, in this. So of course the instruction here is coming out as 32-bit instruction. Then there is a register file. Okay, there are 32 registers in the RISC V, and this is a 3-port register file, right? 2 read ports, 1 write port. So that's why you have registers, read addresses, each 5-bit, A1, A2 and A3. A1 and A2 correspond to the read port, RD1 and RD2, and you give some, you decode the registers address that you need, give 5 bits to A1, you will get the data on RD1 after a fixed constant delay, right? What is that delay? It's basically the time needed to decode this address and the tri-state inverter to read the data out for you, and data will be put out on that 32-bit bus, right? So the read here, we are assuming, very important, it's a combinational read. Let me remind you of that. It's a combinational read, okay, and a sequential write. Now, if we did not have a combinational read and we had a sequential read, for example, it's not sufficient just to give the address, but you need a clock edge to sort of read the data out of the register file. That could also exist. You cannot implement a single cycle processor. I'll highlight this later as well. Okay, so keep this in mind. Finally, you have a data memory. What is a data memory? This is like I told you, right? In the x86, we saw stack, we saw data segment, extra segment. You know, that's where data is actually stored, right? Where you're going to store the array elements, local variables, all of that is going to sit in this memory. Again, you can either read from that, okay? You can read from the data memory by giving an address, and you will get the data on RD port 32-bit again. Or you can give a write data and the address, and then you pulse the clock and the write enable, you will be able to write data into the data memory. Okay, the instruction memory we are assuming here is sort of read only, which means that the code has got written into the compiler, has compiled the code, it has written it into the memory, instruction memory, and while the program is being executed, there is no change in the instruction memory. That's what we mean. Whereas in the data memory, while the program is being executed, you will see that data can change, local variables can change, stack can change, and so on, right? So that's why we are assuming that this is just read only. It's only a read port that is needed for the instruction memory. So let's now look at the single cycle RISC V processor. Okay, so in order to implement any processor, what we need to do is first implement a data path and then the control path separately. Okay, so let us look at a simple a program that we want to, that we are going to execute, and based on this we will try to design the data path basically, right? So essentially, if you look at it, so there is a, see, these are the kind of instructions that we said we are going to implement, right? So if you look at it, there is the load word, which is I type. Then there is a store word, which is S type, which is its own type, right? Again, depending on the, like I said, these instructions are categorized based on the number of registers and the way you actually access them. Okay. So load word, for example, is you're going to calculate an address and then come back and write into this. So there is a destination register needed. Okay. Store word, there's no destination register because you're taking the data from a register and putting it out into the memory, right? So that's why that's a different type. Or is just an R type instruction, 3 registers, 2 source, 1 destination, right? And finally, we are doing a branch and equal to L7. This is the address here that we want to go back out there. Okay, so this is how, and what is shown on the right here is basically the 32-bit machine code that we have, and which is going to sort of sit in memory in hexadecimal like this. This will be 0x, let me just put that out. Okay. Yeah, so what we'll do is we will start with the simple load word instruction that we have, and we are going to just implement the components that are needed for that. Then we will look at the other instructions and add more and more elements and compute elements as needed, or decode elements as needed. So what is the instruction here? LWX6 -4 X9. So what is this going to do? It's going to take X9 register, contents, it's going to subtract 4, treat that as an address, get the data from data memory, write it back to the register X6. Okay, so that's why you have one destination register and a RS1 register with some immediate data that you are going to either add or subtract or whatever. So if you look at this instruction, right, the OP is basically first 7 bits is going to tell you that this is I type instruction, okay, and you have a destination. Therefore, the 8th bit 7 to 11 needs to be interpreted as the destination register. 12 to 14 is function 3, 15 to 19 is RS1, and the last 12 bits are basically the immediate data that you're going to do. Okay. So the first step in any microprocessor, right, is, remember what we are basically saying is that these instructions are sitting in your program memory. Okay, 0xFFC4A303, 32 bits. Next you have the next instruction after 4 bytes, and so on, right? So there is an address called 0x1000, right, which basically has this machine instruction, and therefore the program counter is going to get loaded with this instruction first and say start executing from this point. Okay, so what you're basically saying is, look, your next instruction, you're telling the computer the next instruction is out here. Okay, so that's why this one is called PC next. It's a program counter value for the next instruction, not the current instruction. You are giving that to the program counter, and then the clock is going to pulse. So what we are basically saying here, if you look at the timing diagram of this implementation, right, is here the clock like this, right, clock is here, and then you have the PC next, okay, where we have gone and set it to some particular value like this. Okay, 0x1000. Remember that you have to write this data into PC next before the clock edge, a setup time at least before the clock edge, right, so that it is ready and then you read it. So what will happen is the PC, which is basically the output of this PC register, right, that's going to latch on this data exactly after the clock edge. After, there's going to be some delay and you will get this 0x1000, right? Sorry. Okay. So what we have therefore done now is given this 0x1000, right, on the clock edge, it has latched that data, and then the instruction memory now has the address available. Remember, the instruction memory and the data memory, just like your register file, is combinational read. That means as soon as that address is available, after a certain delay, right, whatever your memory delay is, right, it's going to fetch that instruction, and you're going to fetch this particular instruction 0xFF, right? You see this. This instruction is what is available out here on reading from that location 0x1000. Okay, you have read that and therefore you have fetched that instruction from the memory. The next step is to sort of, start operating on that particular thing, right? So what is the information that is present in that opcode, in that machine code that we see here, right? You look at this. So for that we'll come here. It's saying that the source register. So what are we going to do? We are trying to read the source operand from RS1. Where is RS1? It is sitting here, and that's why fields 15 to 19, right? Fields 15 to 19 are going to represent the source register RS1, and that's why you see that number here being given to A1 of your register file. Okay, that's why the data that is coming out is 9, which corresponds to this 01001. Okay, that's the data that is coming out. We are dealing with register X9 here. Okay, and then again here remember the clock is not needed anymore. Okay, we needed the clock to pulse only once so that the program counter could latch that data, the PC next, and then start reading it. Okay, and after that the clock is technically not needed. Okay, so therefore you're going to take this A1 address, and then the data after a combinational delay will be available at this point. What is that data? It happens to be some 0x2004. Okay, that register X9 happened to contain this data 0x2004, right? Now what do you do? I am now going to take this source register value and then add or subtract with that immediate data, right? Whatever, I'm going to do some arithmetic operation with that immediate data, and therefore the immediate data first needs to be sign extended. Like I told you, the immediate data is only 12-bit. Okay, 0 to 11, immediate of 0 to 11, and that is not, I cannot operate, it's not compatible to do arithmetic operations with that data, 12-bit data and 32-bit numbers, because the register gives me a 32-bit number. Therefore you have to do sign extension, and therefore this 31 to 20 is where of the machine code is where the immediate data resides, and that is given to the sign extender. What is that doing? It is just taking the last bit and just extending the sign. So it's actually a very simple operation. It's just copying that bit into all of these things, and it gives you the sign extended number. Okay, so it turns out that this number here is some FFFFC, what, right? So if you look at this, this is C, right? F. Now when I sign extend, I'm going to just sign extend this one all through, and therefore that's all F's, right? Sign extension does not change the value in 2's complement representation. Therefore this is a very valid operation, and you're just extending it like this. One point to note here is, while these 19 to 15 bits were being decoded and operated on to read the register, this sign extension is happening in parallel. Okay, so that is also one big advantage of having a very nice opcode structure like this, where all this is nice and independent. You don't need to decode anything to figure this out. The data is in the register is just available as an address. You pass it through a decoder, immediate data is there, you process that also in parallel. It helps optimize your cycle time. Okay, so having extended this immediate data, what you now need to do is to operate on these two numbers, the register plus immediate, and get the result. Now who is going to operate on this? You are going to use the ALU to operate on this. Okay, remember that in this particular operation, load word, the address needs to be calculated of register plus immediate or minus immediate, whatever it is. But after you fetch the data from the data memory, it is only being written back to a register. There is no ALU operation being done on the data that is being fetched from the memory directly, and therefore the ALU can be reused here for this arithmetic operation, address calculation purpose, without worrying about having to compute and do some computation on that data. Okay, so that's why this RISC V type of architecture is also called a load store architecture. And if you did not do this, you would need another ALU to actually do this data manipulation separately. Okay, so the ALU control, right, if you look at it, is going to tell you how to operate on this particular data, right? So what is this ALU control? It is sitting in fields of this function 3. Okay, and it is essentially what it is going to do is it is going to get you this 3 bits of information, right? So 0 0 0 is add, 0 0 1 is subtract. You can do AND or. So if you look at it, the address manipulation, address calculation is not complex. You're going to add, you're going to subtract, or some AND or some very minor simple. That's why this function 3 field has only 3 bits, because you don't need all this multiplication, division and all that, right? The actual ALU operations that you want to do will come in the register operation R type, which has that 7 bits. Okay. Anyway, so you now take the source A coming from RD1, which was determined by RS1 register in the opcode, and then this immediate data is going to come to the source B and you get the ALU result. So this result that you have calculated now, right, is essentially going to be the the address of the data memory that you want to fetch data from. Okay, so what you now do is you take that ALU result, which is the address, and feed it to the read port, the address port of the data memory, right? And you feed it, and after some delay you will basically get the data out. It turns out that this data sitting in the memory was 10, right? And that read data is going to come out of the memory, data memory, and now what do you want to do? You want to write this back into the register. Which register? It turns out in this case you want to write to X6. Okay, so therefore this read data 32 bits is actually obtained from the data memory and connected back to the write port of the register file. Okay, now the write port is specifically used only for the write operation, and of course it will get enabled only through the write enable. So this is a very important, combination that needs to determine which register you will write into and when you will write into it. Okay, so what is very important is, yes, you need to pulse this write enable, right? And you also need a clock, because the register file is a sequential write. It is only a combinational read. Okay, so this completes the sort of the data path that we wanted for this load word instruction, right? Now what does the program counter do? Right, the program counter has, you initialized it to 0x1000, right? Where is the next instruction? It is just 4 bytes away, because right now we don't have any branching. We have just implemented load word, right? That means the next instruction could be another load word sitting 4 bytes away, and therefore all you have to do is take the program counter value, add it with 4. That's where the next instruction is, and you get PC plus 4 here, which is given to your PC next. Okay, so this is exactly what is going to happen. And again, I'd like to remind you that as soon as this PC value is ready here, right, this adder will just add 4, and well before the load word instruction is completed, PC plus 4 will be ready. Okay, so if you look at this, PC is here, okay, my PC next, if you look at the control signal here, right, PC plus 4 is actually the PC next. So as soon as my PC gets this, right, this will become plus 4, 0x1004. Okay. So with that, we have completed the data path implementation of the load word instruction.